네. Hello everyone. Good morning. This is Jeong-Gi from the School of Energy and Chemical Engineering at UNIST. So now you are participating in the UNIST carbon neutral international webinar on carbon neutrality, hosted by the UNIST Carbon Neutrality Institute and the Office of the Public Relations. So today we have the fourth webinar on the carbon neutrality, and especially we have invited speaker Professor Kyu Lim from the State University of New York with the presentation title of the Photoelectrocatalytic chemical transformation for lignin depolymerization. Before starting the webinar, I'm going to briefly introduce the biography of the Professor Kyu Lim. He is now assistant professor of the chemistry at the State University of New York, and before getting this position, he got a BS degree in chemical engineering at Hanyang University in 2002. And then he moved to the United States to obtain his PhD degree in organic chemistry at University of Houston. And then he spent 3 years in the industry, LG Chemistry in Korea. And he moved back to US to do his postdoc research experience with the Professor Kirk Shane, who is editor-in-chief of the ACS Applied Materials and Interfaces. After spending several years, he was appointed as an assistant professor at the Department of Chemistry at SUNY, ESF. And then he is also affiliated with some university in Korea, Seogang University since 2020 and Dongguk University since 2021. And he is also working as a member of the editorial advisory board of the ACS Applied Nanomaterials, and he wrote many papers and book chapters about the lignin and biomass. And he got many the honorary award and fellowship. Some notable examples include the U.S. Air Force Research Lab Fellowship in this year and Syracuse Faculty Fellow this year. So this is brief biography of the Professor Kyu Lim, and let's welcome Professor Kyu Lim with a big hand. Okay.
Thank
Please
you
share
so
your
much.
screen. Okay.
Sure. Thanks so much for the introduction. Let me share my screen. Let's see. Right. Let me go to the first page. Right. Here you go. Full screen. Right. Right. Okay.
Yeah.
So first of all, I'd like to thank you, Dr. Professor Jeong-Gi, to invite me to give this talk, and also UNIST. So today's talk is more focusing on photoelectrochemical transformation for lignin depolymerization. I'm training the organic chemistry and polymer chemistry, but for today's talk, I'm more focusing on some kind of the material science for lignin depolymerization. So before starting my talk, let me just introduce my school. So State University of New York, Environment Science Forestry, SUNY ESF is located in Syracuse, New York, in New York State. So once you go to, once you drive 1 hour, so you can go to Canada, or you drive to the west, you can go to Niagara Falls. Once you drive to the east, you can go to Manhattan. I think this is a really good place to go traveling. So SUNY ESF is located in Syracuse, New York. This is our campus. As you can see, there are, let me use my laser points. There are so many trees near our school. So SUNY ESF, as you see the name of our school, Environment Science and Forestry. So our school is very famous for the paper engineering or lignin chemistry. So that I'm working at the second floor of this building. So this building, all the chemistry faculty are working in this whole building, right? So let's move on. Right. So let me give you a brief introduction of lignin. I think I'm not sure you everybody is familiar with the lignin. So that let me give you some background, the introduction. So that we are very interested in replacing the petrochemical by using the biomass, right? So we can obtain a lot of aromatic compound from naphtha from oil refinery. The question is, what if we, replace with the bio-based aromatic compound? So as you may know, the lignocellulose is composed of three components: hemicellulose, cellulose, and lignin. Especially this is structure of lignin. As you can see, there are multiple abundant the aromatic groups. So what if we break down, CC and CO bond, and what happens? So as you can see, there are multiple aromatic compounds. So lignin is the second most abundant biomacromolecule in nature. This is non-eatable biopolymer. So this is the price of lignin, just only 18 cents per kilogram. But once you convert to value-added chemicals, we can produce $85 per kilogram. So that means we can replace with those petrochemical-based aromatic compound, not only aromatic compound, but also aviation fuel, as well as some kind of aliphatic carboxylic acid and so on. So I'm very interested in using renewable materials, for example, lignin, and the solar energy conversion by using electrochemical reactor. So why don't you, incorporate renewable material and sustainable resources such as sunlight and producing bio-based chemicals such as plastic, biofuels, and value-added chemicals by using electrochemical reactors. So today I've specifically talk about photoelectrochemical system. So let me read one sentence. So electrochemistry possesses a number of possible advantages for chemical conversion and biomass sterilization in particular. So today my talk is more focusing on lignin depolymerization by using photoelectrochemical process. So let me introduce about the lignin structure. So here's a lignin structure. So that, as I said before, there are multiple aromatic compounds. So we are able to obtain the phenol or dimethoxy benzene, or not only that, but also we can obtain the dimethoxy, benzoquinone. Those are the very valuable chemicals. So after demethoxylation, and they form the dicarboxylic acid or diketone dialdehyde. We also obtain the aliphatic chemicals. So that lignin is very, very useful. The renewable materials, once we can break down those CC and CO sigma bonds. All right, so what are the cleavage products? So we can obtain the polymer chemicals, those fuels. Especially, I'm very interested in producing aviation fuel from lignin depolymerization. I'm currently working with the US Air Force Research Laboratory. They are highly interested in the production of aviation fuel from the biomass. So I'm closely working with the US Air Force. So that just use lignin and those photoelectrochemical reactor to produce those kind of polymer chemical fuels. All right, so today I'm mainly talking about photocatalysis, photodynamics, and dye sensitive photoelectrochemical cells. So let me talk about why the dye sensitive photoelectrochemical cell is very useful for lignin depolymerization. I'm going to talk about very detail about these spec system. So, my research group we are doing a lot of, molecular simulation in order to understand mechanism pathway. I think this is really, really important for us to understand, sigma bond cleaves. So that the last year, we successfully cleaved the sigma bond, and we produced selective those dimethoxy benzoquinone products. So we got a really good, high selectivity, selective those the aromatic compound. So this compound, as I said before, this is value-added chemicals. I checked the aldrich, so 25 grams for this chemical. The price is about $300, but 25 grams of lignin is only 0.45 cents. So that's why the people are interested in lignin depolymerization in order to get those value-added chemicals. But the challenge is that how do you break down those CO, CC, and CO, sigma bond with really good selectivity and excellent yields? That's a problematic. So today I'm not going to talk about those mechanics study and those applications. Today I'm more focusing on photodynamics and this spec system. All right, so I have 30 years research plan. So this is my phase one, just 10 years plan. So for 10 years, I'm mainly focusing on mechanics pathway, CC and CO bond, sigma bond cliffs in lignin molecules. So very recently, we successfully produced biodegradable superabsorbent polymer materials by using lignin molecules. Not only that, but also we selectively produce 2,6-dimethoxy benzoquinone from the lignin molecules. So currently, we are also working on a phenol derivative and any kind of aliphatic chemicals. So I'm also working with Professor Kwangjin An and Professor Taehyuk Kwon at UNIST for lignin depolymerization. Also, I'm also interested in the synthesis of polyethylene furanate in order to replace the PET plastic. So we can start with the HMF, 5-hydroxymethyl porphyrin. So 5-HMF is able to obtain from the cellulose or lignin cellulose. So we have successfully oxidized HMF to the FTCA by using photoelectrochemical system, and we currently working on the synthesis of PF from the FTCA with the Professor Kwon research groups. So not only that, I have so our research group a lot of experience of CC or CO bonds, sigma bond cliffs. So why don't we use the polymer degradation, especially hydroxylate functional as a polymer, so we can easily break down those CC and sigma bonds. So that this year we start working on those kind of polymer degradation or depolymerization. So that the bottom line is that our lab is more focusing on the polymerization or depolymerization or lignin depolymerization in the next 10 years. All right. So photoelectrocatalytic chemical transformation. So that, like I said, for lignin is the second most abundant biopolymer. So we are specifically interested in photocatalysis immobilized semiconductors. So those chromophore coated TiO2 can be used for photoanodes in a dye-sensitive photoelectrochemical system. So today I'm mainly focusing on those dye-sensitized photoelectrochemical system. So before introducing my research, let me introduce about the UNIST paper, especially on Dr. Zhang and Dr. Yu research group. So they recently published in Nature Communications. So they successfully cleaves beta alpha linkage in lignin and producing vanillin. So vanillin also is very this is a sugar. Vanillin is very value added chemicals. So this is really nice work. So that they describe that they got almost 20 milliamp per square centimeter without any bias in the presence of lignocellulose biomass. That's amazing. I'm very impressed about this research, the paper. But also they produce hydrogen gas almost 5 millimole per square centimeter. They did a really great job for lignin depolymerization by using photoelectrochemical cell using perovskite solar cell. But I'm kind of very interested in how they cleave on CC and CO sigma bonds. That's my research topic. I'm also interested in, instead of using 60, 70, 80, 90 high temperature, why don't you break down those sigma bonds at room temperature and what happens? So as you may know, once the temperature decreases and we can control the reactivity. So what happens once we control reactivity and we can improve selectivity of bond cleavage reactions. That's my interest of lignin depolymerization instead of material science. So let's see. Before 2018, I spent 5 to 6 years to study water splitting reaction by using dye-sensitive photoelectrochemical system. I mean, I checked the schedule of your seminars. I've seen Professor Silver from EPFL or Professor Tilley from University of Zurich. So they are going to be talking about solar-driven water splitting reaction. So today I'm not going to talking about solar-driven water splitting reaction. But let me briefly introduce you about this water splitting reaction and oxidation of the substrate. So on the top, this is water splitting reaction. So that I was a member of Energy Frontier Research Center supported by DOE. I'm working. At the time I was a postdoc working with the Professor Carl Shantz, so that I synthesize, polymer-based ruthenium chromophore as a photocatalysis. So PC stands for photocatalysis, and EC stands for electrocatalysis. So that means for water oxidation catalysis, for water splitting reaction, you have to use water oxidation catalysis. So there's a water oxidation catalysis and there's a photocatalysis. What they're gonna do? So they introduce, this is a kind of assembly system. So electrocatalysis and photoelectrocatalysis, they're covalently, they're bonding each other, so that those assembly system, chromophore catalytic assembly system, is immobilized on the surface of TiO2. That is a photoanode. So in order to split the water molecule, how many number of protons we need? So there are 4 electron transfer. What about the oxidation of organic molecules? Just only 2 electron transfer. For water oxidation, so we have to use aqueous phase. For organic molecule oxidation or lignin degradation or lignin oxidation, we can use organic. So it depends on how you do the surface treatment of lignin, but you can do the non-aqueous phase. But the most challenging for water splitting reaction is that the stability of those assembly systems. Depending on the pH, so they can hydrolyze and detach from the surface, or they can be photo bleaching, and there are a lot of challenge in terms of stability under the light or under the applied bias. Also, the most challenging part is that 4 electron transfer. This is a sequence of 4 electron transfer. So the idea is that why don't you use this spec system for lignin depolymerization or oxidative cleavage of lignin? Because so there's only 2 electron transfer. This is non-aqueous phase. So what is the importance of non-aqueous phase? So you can increase the stability of those anchoring group of photocatalysis. Not only that, we can prevent photo bleaching of photocatalysis in non-aqueous phase comparing to the aqueous phase. Right, so previously I synthesized novel polymer materials, so polychromophore molecules. In the future, I'm very interested in bring those polychromophore molecules as a photocatalysis for lignin depolymerization. But for now, I'm not gonna talking about those polychromophore. So we attach those single ruthenium chromophore to the photoanode. That I'm gonna focusing on today. So. So now let's move on to photoelectrocatalytic system. So why the photoelectrocatalytic system is important? So let me give a brief introduction of photoelectrocatalytic system. So here's the energy profile for photoelectrocatalytic oxidation. So in order to oxidize organic molecules, you have to apply the bias more than 1.2 volts. This is high energy. This is high overpotential. So those overpotential is essential to overcome those kinetic or thermodynamic barrier. The problem is that after heterogeneous single electron transfer to the anode, and then what happens? There is formation of radical cation. So this is problematic. So radical cation intermediate allows for decomposition and side reaction of organic molecules. Because it's high overpotential, that's problematic. So the question is, can we avoid the formation of radical cation intermediate? The answer is yes. How do we avoid them? Because we can decrease the overpotential, and then we can solve the problem. But the problem is once you decrease the overpotential, so that means we're not gonna have any oxidation of organic molecules. So we need a certain overpotential. But there's a way to decrease overpotential. Let me explain about how we reduce the overpotential. And this is the first problem. The second problem, okay, there are two issues for electrocatalytic oxidation. First, the formation of radical cation, and second, accessibility. So this is a lignin molecule. This is a biomacromolecules. That's a huge molecules. And there's active sites here, here. So there's active sites. So as you can see, this is a benzylic secondary alcohol and aliphatic primary alcohol, right? So this is the place where we break down C and CO sigma bond. The problem is that, so let's take a look at the surface area of those anodes. So that means there's a reaction happens at a surface of this anode. So let's say you have large biomacromolecule on the right side, and you have this small surface area of anodes. The problem is that there's a limited accessibility, right? So that means, catalytic activity is gonna be limited because of the size of the molecules. This is also one of disadvantages. But the question is, how do you overcome those two challenges? So let me introduce about photoelectrocatalytic oxidation with the aminoxyl radical mediator. So this is a callus. So this is ruthenium, the metachrom of callus. So ruthenium, the metachrom of callus is immobilized to the semiconductor. And what happens? The excited molecules then photoexcited electrons inject to the conduction band of TiO2, and the electron is traveling from anode to the cathode. And then at the surface, so this is an oxidized chromophore or oxidized matter. So this is strong oxidizing agent, right? Kind of, strong. This is oxidized ruthenium chromophore on the surface of anodes. So what happens? So there's a whole transfer from those photocatalysts to the aminoxyl radical mediator. So what happens? And they oxidize to form oxoammonium. So those oxoammonium is strong oxidizing agent. And then after that, there's 2 electron transfer to the substrate. It's going to be benzyl alcohol, any lignin, or any organic molecules. So then what happens? They're going to oxidize. And then there are 2 electron transfer to oxoammonium. So they can be reduced to, regenerate the original form of aminoxyl radical mediator. This is kind of cycling process, right? So that means we don't have to keep adding those, aminoxyl radical mediator. This is a perfect system, unless they don't have any photobleaching or they don't have any, degradation of those molecules, right? So as you can see, there are 2 processes here on the surface that are heterogeneous electron transfer and homogeneous, proton electron transfer. So there are 2 processes. So what are the advantages of this system? So we can significantly decrease the overpotential at room temperature. So now, previously we need 1 voltage, but once we use some photo of light and those mediator, we can significantly reduce the overpotential, even 0 voltage, and we can oxidize molecules. That's really good, right? So, and what happens? We don't need any, there is no formation of radical cation. Let me show you in the previous here. Yeah, there is no formation of radical cation, right? Because of the presence of those aminoxyl radical mediator. So once they oxidize, oxoammoniums can be a very strong oxidizing agent, so that they can be oxidized, those organic molecules, so that we can improve, reaction selectivity with the lower applied potential. So let me read out those sentences. Photoelectrocatalytic oxidation under mild conditions, especially at room temperature, can provide excellent selectivity for the desired oxidized product and help to improve existing oxidation method. So I'm more interested in control the reactivity. That means we can enhance selectivity of wanted product or targeting molecules. That's my main interest. So let me give you some examples. So here's the example of slides. So on the top is chemical oxidation with the high temperature 100 degrees Celsius under the oxygen 24 hours. So we can oxidize alcohol to the ketone. And this electrocatalytic oxidation, alcohol to the ketone, we need more than 1 voltage. And electrochemical oxidation with the electrocatalysis, this kind of mediator, we can reduce the voltage 0.74 voltage. But this is the system of photoelectrochemical process with those nitrogen mediator. So without any bias, there's internal bias, definitely internal bias. I'm talking about 0 voltage versus HH plus, so that we can successfully oxidize alcohol to the ketone. But you can use any method to oxidize alcohol to the ketone. But the question is, what if we have macromolecule, what happens? Once you use a high temperature, and you can break down CO sigma bond, and there's a formation of radical, and then there's recoupling reaction. So this is a side reaction. So side reaction is problematic because they reduce the selectivity. Also, they significantly decrease the yield of the product. So that's why I'm interested in photoelectrochemical oxidation under mild conditions, especially at room temperature. All right, so this is another advantage. So once oxidized to oxammonium, so here is the active site, right? So that's here is the active site. So those oxammonium is easily accessed to those active site in those lignin molecules. The reason is that those oxammonium is soluble in solvent. But photocatalysis is attached to immobilize to the photoanodes, so they don't have to hang around in a solvent, right? So this is heterogeneous photocatalysis. So those allow to oxidize amine radical to oxammonium. Now oxammonium, this catalyst is electrocatalysis. So this catalyst is dissolved in a solvent, like a soluble oxammonium. So soluble oxammonium is reduced by those active sites and to regenerate those original form of amino radical. Okay, so let me just sum up the let me just make some summary. So what is the advantage of photoelectrochemical system? The first, so there's no formation of radical cation. And then those photocatalysis is immobilized to the surface of anodes. This is a heterogeneous photocatalysis system. And then this homogeneous amino radical mediator is able to contact the active site in those biomacromolecules. So these are advantages. So in addition, so we can significantly reduce the overpotential from 1 voltage to 0 voltage. So that we can control the reactivity of those secondary alcohol or benzylic alcohol. So there are 3 advantages of this system. So that's why I research is highly interested in photoelectrocatalytic oxidation with electron proton transfer mediator. Right. So also not only photoelectrocatalytic system, we are also interested in thermochemical oxidation at high temperature. So very recently, we developed a novel catalyst system by using thermochemical oxidation. So we obtained multiple aromatic compound or those aliphatic dicarboxylic acid and their derivative products. So we obtained multiple products. The problem is they have a very low yield of each product, right? So what if we use photoelectrocatalytic system in order to increase, to obtain specific compound? Well, what if we specify cliffs C alpha, C alpha beta, or C beta oxygen, so that we can specifically obtain targeting molecules? But under thermochemical oxidation, it's really challenging to produce targeting molecules. However, once we use those photoelectrocatalytic system, we can have targeting in a bond cleavage reaction, the bond cleavage reaction, so that as a result, be able to obtain targeting or wanted aromatic chemicals, right? All right, so this is kind of example of thermochemical oxidation. So high, this 120, 180, that's at on the high temperature, as you can see, the multiple product because of recoupling reaction. But there's some example of room temperature reaction, the science, nature. So once we break down those CO6 bomb at room temperature with excellent yield, I mean, that's really great because we overcome major challenges. So what are the major challenges? So major challenges are high yield and selective production of aromatic chemicals from lignin. So now let's talk about bond breaking process. So I'm pretty sure everybody took organic chemistry 1 in a college, right? So this is the SN1 reaction mechanism. So in the step number 1, right? This is what the protonation. So as you can see, the activation is very small. That's very small. So there's small activation energy, and this is the ectothermal reaction. However, so loss of leaving group, this is the H2O. So OH, hydroxy is not a good leaving group, but H2O is really good leaving group. But this is a bond breaking process. So H2O, those H2O is, break the bond of C sigma bond. So this is a bond breaking process. So there's large activation. This is endothermic. They need energy. They have to absorb the heat energy in order to break down the C and carbon oxygen sigma bond for loss of leaving group, right? So this is a convert from alcohol to the alkyl halide, and alkyl halide to alcohol, the same thing. This is the largest activation energy. So that's why the bond breaking process is a rate determining step. So, but the bottom line is that the bond breaking process is the most challenged. They need some energy. They have to absorb, heat energy, heat, light, or any electricity. So here's another example. I think last decade, people are focusing on oxidative cleavage of CO bond because of low bonding dissociation energy. So CO bond in the beta alpha link, I'm gonna talk about beta alpha links later, but anyway. So CO sigma bond, the bonding dissociation energy of CO sigma bond is about 70 kilocalorie per mole. So that's why multiple the paper manuscript they describe oxidative cleavage of CO bond in beta alpha linkages because of lower bonding dissociation energy compared to the bonding dissociation of CC bond. So bonding dissociation and CC bond is about 90 or 83 to 90 kilocalorie per mole. Even CF bond is the highest. This is 115 kilocalorie per mole. But anyway, I'm also interested in degradation of those in PFS or CF bond. But today I'm not going to talking about those bond decleavage CF bond. I'm more focusing on CC bond. All right, so chemical review 2021, there are 2 papers in the same year. So develop the CC bond cleavage process suffer from some limitation, require harsh condition. I showed the example before. However, selective control CC bond cleavage under mild condition remain a formidable challenges. All right, so like I said, before 2018, I'm more focusing on those, these water splitting reaction. I mean, I think I had this typo. This after 2019. So now I'm interested in photoelectrocatalytic system. So now introduction, I'm background, I gave a some idea why I'm interested in those photoelectrocatalytic system with the mediator. So before move on to today's talk, let me briefly talk about water splitting reaction because I just want to introduce about some polymer-based chromophore molecule because you might be interested in those molecules. This is kind of a novel molecule that I developed in the last 5 years, from 2013 to 2018. All right, so this is polyphenylbutadiene-based polychromophore. So this is polymer backbone, right? Okay, so green benzene aromatic, link the chain. This is a polymer backbone. And here, the orange sphere, this stands for chromophore, pigment, or dye. So those chromophore attached to the polymer backbone, right? So then there are 2 types of chromophore, or there are 2 types of callus. So callus or chromophore is far away from the TiO2, and another chromophore or callus is near the TiO2. So there are, couple types of chromophore or callus. So what happens once it excites those molecules, right? So then this unbound chromophore, and there is an intermolecular energy transfer among those polymer backbone. And what happens? And those photoexcited energy is transferred to the chromophore that is attached, that is immobilized onto the TiO2, and there is an electron injection. So that means the negative charge is staying in the TiO2 and the positive charge on a polymer backbone. So there's charge separation. So charge separation is extremely important for water splitting reaction, right? So there are a lot of research to prevent charge recombination. What happens charge recombination? So -1 plus 1 is 0, neutral. So that means there's no way to oxidate water molecules. That's problematic. So that's why people are interested in charge separation at the surface of those PI semiconductor. So this is just to oversimplify the scheme. So this is ruthenium as a chromophore. Once they absorb the photon of light, they go to the excited state. This is a redox potential, and the photoexcited electron is inject to the conduction band of TiO2 and ruthenium to the ruthenium-3, and there's whole transfer from water oxide catalyst to those ruthenium. So ruthenium-3 to the ruthenium-2, right? So they fill the hole, and this water oxide catalyst split the water molecules, right? So that I observe photodynamic events by using transient absorption spectroscopy. So that we observe energy transfer, Hall transfer, electron injection, depending on the time scale. Usually electron injection is very fast, it's picosecond, and the Hall transfer is picosecond, and I'm sorry, the electron injection is around femtosecond. This picosecond, energy transfer is nanosecond to the microsecond. So based on those time scale, we are able to propose photodynamic events at the surface of TiO2. So this is the this is the photophysical events at the surface of TiO2. So I think I explained about those scheme before. As I said before, so those chromophore absorb the photon of light, and then the ruthenium is near those chromophore near the TiO2, and then there is electron injection TiO2. However, so another ruthenium is far away from the TiO2, and there's an intermolecular, I'm sorry, not the intramolecular energy transfer along the polymer backbone. So that there's the energy transfer, then those ruthenium nearby TiO2, then there is electron injection, Also definitely there are some charge recombination between those ruthenium-3 and ruthenium-1. All right. So that's my plan. I mean, currently we are using just single those chromophores, so that later on we are interested in introduce those polymer-based ruthenium chromophore to TiO2 as a photoanode for lignin depolymerization. Right. So today, before introducing about two topics, so let me give you some idea of what is alpha, beta, gamma. There's alpha carbon. So alpha carbon, as you may know, hydroxy attached to those carbon, we call alpha. And then the beta carbon is next to the alpha carbon, and this gamma carbon. So alpha, beta, gamma. And here, this is secondary alcohol, this is aliphatic primary alcohol, and this is oxygen, the ether linkage. So that's why we call them beta aryl ether linkages. So on the bottom right, so this is a lignin model compound, the structure of a lignin model compound. But you have to pay attention to secondary alcohol, primary alcohol, as well as those hydroxy on para position. So those three hydroxy is really, really important to control or to break down on CC or sigma bond. So depending on the depending on the content of secondary, primary, or hydroxy on para position, and we can able to control the breakdown of CC, C or sigma bond. I'm gonna talking about review those concepts in part 2. So I think I talk about secondary alcohol, primary alcohol, and hydroxyl or phenolic or non-phenolic. So without hydroxyl on para position, we can call the phenolic lignin compound. So if there is more content of hydrogen on para position, we can call them as non-phenolic or the methoxy non-phenolic. So phenolic and non-phenolic, the content of phenolic and non-phenolic is really, really important to cleave the C alpha, C alpha beta, or C beta oxygen cleaves. All right, so I spend a lot of time to talk about the background of my research. So let's talk about my research. Let me split the two parts. This is part one, solar-driven intermolecular energy electron transfer at the interface. So part two, I'm going to talk about mechanics of pathway of CCO, sigma moment very briefly. All right, so the question is, why do they interest by PDN? So there are there are multiple reasons. First, efficient electron injection to TiO2, proper oxidation potential, and long excited state lifetime, especially the lifetime of those chromophores is more than 1 micro or 1.2 microsecond in a polar aprotic solvent. So let's talk about the interaction between ruthenium chromophore and TiO2. So that very recently we prepare ruthenium-coated TiO2 nanoparticles. So ruthenium-coated TiO2 nanoparticle to see what happens, right? So this is the absorption of ruthenium chromophore. There's a lambda max is about 460 nanometer in the visual region. So, but in the visual region, there's no absorption. So this gray color stands for without the ruthenium chromophore, and the red solid line stands for ruthenium-coated TiO2. So you clearly see metal ligand charge transfer absorption at 406 nanometer. So this metal ligand charge transfer at 406 nanometer. So I think I mentioned before, so ruthenium is a proper oxidation potential because of redox potential is higher than the conduction band of TiO2. That's why after photoexcitation and the photoexcited electrons you inject to the conduction band of TiO2. All right, so let me show the some transient absorption spectroscopy. So this is the absorption band of bipyridine radical anion. So what is bipyridine radical anion? So this is bipyridine. So there are two pyridine. So that's why we call it bipyridine. So after the metal ligand charge transfer, what happens? There is formation of radical anion. So that is bipyridine radical anion. So this is the absorption band of bipyridine radical anion. However, as the time goes by, from 1 picosecond to the 1.2 nanosecond, what happens? So there is significantly reduce the absorption of bipyridine radical anion. What does it mean? So that means electron from bipyridine radical anion, those electrons from bipyridine radical anion is transferred to the conduction band of TiO2. That's what that means. So the decay of absorption at 385 nanometer. So that means there's a intermolecular electron transfer to the TiO2 after photoexcitation with ruthenium chromophore. So after photoexcitation of ruthenium chromophore, as I said, there's a metal ligand charge transfer. That's why bipyridine obtained one electron to form the radical anion. Then after that, there's electron transferred to the conduction band of TiO2. So there's a direct evidence of intermolecular electron transfer to the TiO2, so electron injection. So there's a direct evidence by using transient absorption spectroscopy. So let me show you some control experiments. So this is a control experiment. So instead of using TiO2, what if we use a zirconium oxide? So because the conduction band of zirconium oxide is higher than redox potential of ruthenium chromophore. That means even though after photoexciting ruthenium chromophore, ideally there's no electron transfer of zirconium oxide because of higher conduction band of zirconium oxide compared to conduction band of TiO2. Let's see what happens. So on the right, this is like I said before, at 385 nanometer, this absorption of bipyridine radical anion. So as times go by, like from 1 picosecond to the 1.2 nanosecond, so there's no decay. So what does it mean? So that means there's no electron transfer, there's no electron injection to the zirconium oxide. So this is a direct evidence of electron injection, photoexcited electron injection to TiO2 by comparing the large band gap of zirconium oxide. I think this is a really good experiment, I think. So then based on that, okay, so now we understand the electron transfer to the conduction band of TiO2. That's great. So and to see what happens, this is the static photophysical property of ruthenium chromophore at the surface of TiO2. Once excited ruthenium molecules, and there's electron transfer. And this is quenching. So as you can see, there's huge quenching. And there's a dramatic decrease lifetime, because lifetime ruthenium chromophore was 1 microsecond. However, after excitation of those ruthenium chromo TiO2, lifetime is significantly decreased from 1 microsecond to the 280 nanosecond. So that means this is another evidence of photoexcited electron inject to the the conduction band of TiO2. So based on that, the ruthenium is oxidized. And what happens? There's a whole transfer from ruthenium to the amino oxide, the mediator, right? So let me read out the 3 bullets. The first, light absorption, electron injection from ruthenium to the TiO2 surface. Second, oxidation of ACT. ACT means amino oxide radical mediator to form oxoammonium by ruthenium-3, the oxide ruthenium on the surface, the ground state ruthenium-2. So then this is the last step. So HAT stands for hydrogen atom transfer oxidation of substrate by HT, regenerating the hydroxyamine radical. So those the amino oxide radical is reduced by those lignin molecules. That's the very idea. This is kind of proposed the mechanism. So now, we test the series of amino oxide radical mediator. All right. So let me show the 3 amino oxide radical mediator. This tempo. This is very common oxidizing agent in the industry. And then the ACT, 4-acetamidol tempo. So that means there's acetamidol is attached to those in this position, para position. And here, this is a bicyclic. So on the left, this is a monocyclic. On the right, bicyclic. I'm kind of interested in steric effect of nitrogen mediator. Also, as you can see, the ABNO, the bicyclic mediator, there's a high redox potential. I'm sorry, not high. This is a redox potential compared to 2 mediator. According to the previous study, because people, a lot of research group, they use those ACT or tempo. They didn't use the bicyclic nitrogen mediator. The reason is that they test lignin depolymerization or oxidative lignin degradation in aqueous phase. So especially ABNO, those bicyclic mediator is not reversible. This is irreversible in aqueous phase. But very interestingly, in non-aqueous system, they got the really nice reversible the peaks. So this is the evidence. But in aqueous system, there's no redox peaks. So that's why the people didn't use those bicyclic nitrogen mediator for lignin depolymerization in aqueous phase. But recently we tested those bicyclic mediator. It works really good. But today I'm not gonna talking about the bicyclic compound. I'm more focusing on monocyclic amino oxide radical mediator because we are still working on this this project. Anyway, so let's talk about those ACT, 4-acetamidol tempo. So I'm also interested in those monocyclic amino oxide radical mediator. The reason is that there's an electron transfer to form the oxoammonium. So let's take a look at those functional group. This is the amide group. This is electron-withdrawing group. So what happens? So those electron-withdrawing group is pulled electron density from oxoammonium. So that means this is not stable. So that's why this is strong oxidizing agent. Right? So strong oxidizing agent is easily oxidize any organic molecules. So that's why I'm interested in those amino oxide radical mediator because of the presence of the electron-withdrawing group on this 4 positions. All right, so now why don't you talk about the interaction between those photocatalysis and amino oxide radical mediator? The same experiments. So ruthenium is dissolved in non-aqueous medium, and then we added those ACT into the solution. And what happened? There's huge quenching effect. That's great because under the light, under the light illumination, especially visual light illumination, it's one-cell illumination, there's a significant quenching effect. So that means this ruthenium, the photoexcited ruthenium chromophore is quenched by amino oxide radical mediator. So that means there is a energy electron transfer between photoexcited photocatalyst and nitrogen mediator. That's really great. So that's really great quenching effect. right? So in the lifetime, this lifetime measurement is consistent with quenching experiments, right? All right, here's the last part. Then we assemble the cell. So here, ruthenium coated TiO2 so as a working electrode, and we added those nitrogen mediator to what happens, and also with the lignin molded compound. This is a photocurrent transient measurement. I mean, this is very simple. So right, off, on, off, on, off, on. So under the light, there's a photo response. That means the electron is transferred anode to cathode, they generate electricity, right? So when you increase the ACT, as you can see, they increase the photon density. That means ACT is a transfer electron. That's a good thing. But very interestingly, when you add the lignin molded compound, as you can see, the huge increase of photon density. I mean, this measurement is highly consistent with the data that I introduced at the beginning of my talk, especially Dr. Yu and Dr. Zhang's report in Nature on the communication. So that I'm very interested in what happens, what's the role of lignin molded compound, what is the role of lignin? So I assume that there is lignin molded compound, or those lignin molecules, especially those the hydroxyl. So because of 3 hydroxyl groups in lignin compound, so they can play as a sacrificial donor. That's what I assume. But we are still under investigation role of lignin molded compound. Why they increase the dose photocurrent density? So we hypothesize that so lignin molded compound can be play with the can be play a role of sacrificial donor. So that we are still under investigation, but I'm very interested about those lignin molded compound to see why they increase the photocurrent density. Right. So I think I'm kind of running out of time. So let me quickly, talk about the rest of the slide. So that, as you may know, lignin has a very dark brown colors. So that that's why there's no example of photocatalysis, because once you excite those molecules, so those black brown color absorb all of photon. That's problematic. So and then Jackson and Electrocatalysis, they're talking about the challenge of the wood biomass because of the color of the lignin. I'm not going to read everything, but as you can see, photocurrent is very low because of the color. So those lignin molecules, they absorb all of photon from the sunlight. That's problematic. That's why we got the low photocurrent density. However, we use the backside illumination. That means the working electrode is attached to the wall of reaction vessel. So that means the photon is directly passed through the transparent floating the tin oxide, and there's a reaction happens those at the surface of electrodes. So that means amino radical mediator oxidize at the surface of ruthenium chrome 4. Then oxoammonium is going to be activate lignin molecules. So that's amazing, right? So as you can see, there's a dramatically increased photocurrent density by using backside illumination. So now I talk about interaction between ruthenium TiO2 semiconductor or photocatalyst and ACT amino acid mediator. And then let's talk about what happens to lignin molded compounds. Then let's add lignin molded compound and to see what happens. Right. So I'm not gonna read those 3 steps. I've already discussed about those proposed mechanism from a previous study. Right. That's going to be the last part of my talk. Actually, I prepared for 3 parts, but because of time constraint, I kind of reduced the number of the slides. So I'm going to give you just part 2 to let me finish my talk today. All right, so structure of lignin and the molded compound. So I think I talked before this lignin molded compound. There are multiple possible ways to cleave sigma bond, right? I'm sorry, there's some typo. It should be C alpha, not the C beta. C alpha, C alpha beta, C beta oxygen, or O for linkage. So 1, 2, 3, 4. So after that, so there are multiple possible cleavage product, right? Here's the example of cleavage reaction. So they use those catalysts under the light, and even though they're 100%, but they can get the multiple product, right? The question is, can we get just only 2 products? Can you get just C alpha or C alpha beta or C beta oxygen? So can you get just 2 product only? Can you targeting specific molecules? The answer is yes. So this is experiment. So on the left, this is a non-phenolic moiety. That means R prime is equal to hydrogen. On the right, R prime is equal to OH, hydroxyl. So very interestingly, hydroxyl on the para position. So we can cleave CR and C alpha. But however, so without the hydroxyl, that is non-phenolic moiety, we are not able to break down CR and C alpha cleaves. So they can simply oxidize secondary alcohol to the ketone. Anyway, this is GCFID data to show the analysis of cleavage product. But very interesting, we got the 88% of product 2 on the let's see, on the left side, and product 3 on the right side, 88%, 95%. This is really great, selectivity, and then cleavage selectivity is more than 91% at room temperature. I mean, there are a lot of reports of those bond cleavage reaction, but they usually in a high temperature, high pressure, or high the bias. But we don't use any, we don't give any energy or heat energy. We just use room temperature. This is under the Wonsan AM 1.5 G. We use Wonsan illumination at the room temperature in this is under aerobic conditions. So this is reaction mechanism. So I'm not going to go over all the reaction mechanism, but the key point is that the formation of oxy radical on the para position. So then there's a resonance structure here. So then those radical on RD position is from the 5 membrane with the amino oxide radical. So we prove those mechanism by using oxygen 18 labeling. So instead of using oxygen 16, we replace with the oxygen 18. Anyway, we use H2O oxygen 18. This is extremely important, extremely expensive. I don't remember exact price, but I think just few milligrams. It's about $500. If you buy just 1 gram, it's gonna be more than $10,000. It's very expensive. Those oxygen 18 water. But I talked to my student, you got to really be careful because this is extremely expensive molecules. But you have to do those reactions just one time to get those product. But fortunately, she made it, so that's great. Anyway, she synthesized amino oxide radical mediator containing oxygen 18, and we obtain oxygen 18 on product 2. So we can prove those reaction mechanism. Right. So not only that, we test a series of lignin model compound on entry 1 and 2, as you can see, without secondary aliphatic alcohol, right? 1, 2, 3, and 3. As you can see, this is methoxy on the left side, and entry 4. This is a mixture of secondary benzylic alcohol and primary aliphatic alcohol without the methoxy. So entry 5. So methoxy, this is non-phenolic. So 1, 2, 3, 4, 5, 6. So those 3 compounds, there is no phenolic, no hydroxyl on those para positions, right? And entry 6, the dimethoxy on 3 and 6 position. So and then there are secondary and primary. And entry 7, entry 8 is phenolic. So entry 7, monomethoxy, entry 8 is dimethoxy. So not only 8 samples, so we now test the multiple series of lignin model compound in order to understand the mechanism. I think that's really important to understand the mechanism study. In this way, you can design those systems. So anyway, the bottom line is that this phenolic is really important for CRAC alpha cleavage reactions. So not only that, those aliphatic primary aliphatic groups and secondary benzyl group, that's also important to cleave CRAC alpha or C alpha beta or C beta C gamma oxidation. So that this is still under investigation. So hopefully I can share those more data in the later. But today I just want to emphasize that those phenolic, those hydroxyl para positions are extremely important for CRAC alpha cleaves. So without the hydroxyl, we can cleave C alpha C beta cleaves right there. Okay. So this is a reaction, the mechanism. We did a lot of molecular simulation for now in order to understand, CC and CO bond cleaves. let's take a look at on the right side. Yeah, again, C beta oxygen cliffs. I think this is very interesting because once they oxidize secondary benzyl alcohol, so they form the ketone form. So then what happens? So bonding dissociation energy of C beta oxygen is dramatically decreased. I think I don't remember exactly bonding dissociation energy C beta and oxygen, but after oxidize secondary alcohol, then bonding dissociation energy of C beta and oxygen dramatically drop, and then you can easily see beta oxygen cleaves. So you can get the two product at the cathode. So that's very interesting. So this is a two-step process to cleave specifically C beta oxygen cleaves. So we got the more than 9% select cleaves, and we got the more than 9% of each products, right? So like I said before, we do a lot of molecular simulation for now in order to understand those mechanisms pathway. I think I spent almost 1 hour. So let me just give a brief summary. So very recently, we successfully cleave CCCL, the bond cleavage in lignin molecules, but today I didn't talk about the detail of those CCCL bond cleavage to obtain those 2,6-dimethoxy benzoquinone, but we are currently under investigation. I think we spent 6 or 1 year, so we fully understand the mechanism. So because we want to publish paper with the very detailed mechanism pathway of those native lignin to those mono the benzoquinone molecules. So let me read out 2 sentences. So photoelectrocatalytic system offers an effective means of harnessing renewable energy to drive 2 electron, that's remember 2 electron redox process with the lower thermodynamic process barriers. So that means we can significantly reduce the bias, almost 0 voltage versus HH plus. And this photoelectrochemical heterogeneous catalytic process provides a unique foundation to carry out selective CCCO bond cleavage, essential to development of lignin converter technology. So let me introduce about my group members. We did a multiple project in my group, especially I'm also interested in sustainable Lewis-based caloric polymerization method. This is a new method in under air condition because polymerization is, if there's oxygen energy quencher, so that's why people do the polymerization without the oxygen. But with the oxygen, we can control the molecule with the polymer. That's really good. This kind of I'm interested in novel polymerization methods. So this project supported by NSF. So I mean, many of my research group members are working on those lignin depolymerization. So this project is supported by USD. Also, I'm highly interested in interfacial energy electron transfer at the intercellular TiO2. Also, we are interested in chemical degradation, especially of CF bond cleaves. I think carbon floating bond breaking process is the most challenging compared to sigma bond. But I like the challenge. I like those challenging projects. So that's why I'm working on the PFAS degradation in wastewater. I'm not sure about the South Korea and China or Japan in East Asia, but in the US, they started regulation of PFAS, especially Teflon. So I think in Utah State, they started regulation of the PFAS molecules in water, in drinking water. So that the PFAS degradation is going to be really hot issue, hot topics in next 10 years. I'm 100% sure that's why I'm interested in CF bond degradation in drinking water and in wastewater. So that, I mean, everything is related, right? So I'm interested in chemical transformation by using photoelectrocatalytic system. So my research is really by 3 topics: carbon, energy, and water. So today, Xia Li, Senora Kim, Hai, Songsu Park, also I think Udani, I think they are doing all of the work for today's talk. So especially I'd like to thank you for all of my collaborators, especially UNIST, Professor Kwon, Professor An, and then Professor Dr. Sherman, Professor Sherman. I've been working with him almost 10 years. Professor John from University of Texas, Arlington, I've been working with him almost 8 years. Professor Yu, I'm working on with you almost 5 years. Wei Wei Zhang from Syracuse University, 6 years. I'm working on the Dr. Jeju Lee, almost 4 years. Ian Power, Ian Gisov, and Dr. Wendy Lee. He's I think editor of chief in ACS of nanomaterials. And I'm currently working on Chris Bunker from Air Force Research Laboratory. And especially today, Hai, Udani, Shua, Eric, and Serena, they are working on this lignin depolymerization. I want to give all the credit to my student and my collaborator. And I'd like to thank you for supporting my research from National Science Foundation and USDA, especially New York State. So thank you for your attention.
Thanks for the very impressive talk. So if you have any question, you can type your question in the Q&A or chatting window, or you can click raise your hand icons if you want to verbally ask your question.
Mm-hmm.
Okay. Anyway, again, very impressive and interesting talk. So let me ask you some questions. So at the beginning, you mentioned that you are trying to make aviation fuels, right, by the support of the U.S. Air Force. But do you have any unique strategies for making the aviation fuel? I mean, conventionally, many people are trying to make aviation fuels from biomass through the chemical hydrogenation or something like that, right?
This is an initial project with the I kind of initiate those project with the Air Force because they are interested in once you that clips on the CC and CO, then you can produce a lot of aromatic compounds, especially C6 and C12. Once we get those aromatic chemicals, and then you can do some hydrogenation by using catalysis. So then you can obtain the cyclic compound. That's kind of brief idea. So once we got the C6, C12 building block aromatic chemicals, and then we're going to do hydrogenation by using catalysis for to convert to the cyclic the compound.
So I think many seems to be hungry. It's already 12 o'clock in Korea. Let me ask you one more question. So in the last part, you showed us some mechanistic study about by the labeling of the labeling with the O18 actually, right? So similar to the O18 labeling, are there some method to confirm where the proton comes from in electrochemical biomass oxidations? I'm very curious about that kind of thing.
Right. So I think that's the point. So for now, so our research group and other research, so we are working on the synthesis of dimer, trimer, pentamer, hexamer, and oligomers, so that we can control the those lengths of the lignin model compound. So not only that, we're also interested in labeling carbon, isotope carbon 13. So we also label carbon 13 on the lignin model compound, and then we can specifically understand the cleavage reaction mechanism. That's our next stage of research. So that we started with the oxygen 18 labeling because of aminoxidase the mediator. But so in order to understand all the reaction mechanism, we are interested in synthesize lignin model compound containing carbon 13 labeled those lignin the monomer. So then after that, we also interested in dimer or pentamer, tetramer, hexamer. Because I'm not much a science. I'm more interested in those kind of the mechanism to understand what happens for lignin depolymerization.
Okay. So because of time limitation, I think we have to wrap up the webinar. But I will let you know that he's going to give you an offline talk at UNIST in the upcoming November. So if you have any questions and if you are very interested in in his research, you can meet in person at UNIST soon. Okay. And thanks very much again. And let's give him a big hand again. Thank you.
Thank you. Thanks so much.